Hi, I want to welcome you to Fluid and Electrolytes. Let's get ready. So we're going to go through just some basic introductions about the movement of fluid. We're not going to touch electrolytes at all. In fact, we're probably not going to touch electrolytes till next week. So let's first talk about this idea of osmosis. So osmosis is when water moves. It is a membrane that isn't permeable to molecules, so only water is moving. So it is impermeable to the solute, which is the molecule. It is only permeable to the water moving. So what happens is, if you look at this, the ratio, if you look on this screen, the ratio is 6 waters to 4 solutes, which is a 3-to-2 on this side, side A. And on side B, it's 6 waters to 2 solutes, which is a 3-to-1. So the body always tries to maintain equilibrium. So the water, because the solute can't move, the waters are going to move over. And if you move over 2 waters, you then change it as an 8 water to 4 solute load. And that's a 2-to-1 ratio. And then on this side, it becomes a 4 water to 2 solutes, and that's a 2-to-1 ratio. So you'll see that the ratio then is the same, and that's equilibrium. So this is a membrane is not permeable. It's impermeable to solutes, and so only water moves. And the water moves this way because these solutes pull the water to them. So it says side A has a more solute than side B, thus side A has greater osmotic pressure. All right, so that's osmosis. Doesn't take any energy, just happens. Okay, the next slide then looks at diffusion. Diffusion is movement from a higher concentration to a lower concentration as the membrane is permeable. So we can actually use the same example, only now we have a membrane, and that's what this dotted line depicts. Now we have a membrane in the middle that is permeable to solutes. So in this case, side A has more solutes than side B. Thus side A has a greater pressure. In this case, the membrane is permeable. So we will move these solutes over. Whoops, sorry. At least one of them to get the ratio to be the same. So before, the ratio was 6W to 4S, which is 6 water to 4 solutes. Over here it was 6 water to 2 solutes. So you see the difference in the ratio. If I move one of these solutes over, I then go from 6 water to 3 solutes here, and 6 water to 3 solutes here, so the ratio is the same. So again, the whole purpose of diffusion and osmosis is just to get to equilibrium. Facilitated transport or facilitated diffusion does not require energy. So it's another way that items move. Fluid can move, glucose can move. It's how glucose gets into the cell. Facilitated diffusion has glucose transporters and sodium glucose linked transporters that help to move the glucose into the cell. It's almost like it lands on those, dumps it, and goes in. But to activate these transporters, it takes insulin. It does not involve energy. We still haven't gotten to anything that involves energy. Okay, so we're going to move on. These are just all different facets of what fluid does and how particles move. So when we look now at how does fluid move in and out of capillaries, we have to add to this process the idea of pressure. So the capillaries themselves have blood hydrostatic pressure, which is the force of the blood against the wall of the capillary. The more fluid in that capillary bed, the greater the force, the greater stretching, the greater the hydrostatic pressure. And that hydrostatic pressure is what moves fluid out of the capillary into the interstitial space. So all the space around here is supposed to be interstitial space. There's also interstitial fluid hydrostatic pressure, and that moves fluids out of interstitial compartments into capillaries. The lymphatic system also gets some of that fluid from the interstitial space. I didn't put an arrow there, but some of that may end up in the lymphatic system. There is also something, so now we're on our fourth also, called colloid osmotic pressure, or you can call it oncotic pressure. So colloid osmotic pressure and oncotic pressure are the same thing. And that's pressure exerted by proteins. So within the bloodstream, the major protein is albumin. Albumin has a pulling force. It has an oncotic pressure that pulls fluid to it. So all these factors are part of the process of fluid moving in and out of the bloodstream. For example, if someone has a low protein level, they may get edema from that because they don't have that oncotic pressure of the proteins in their bloodstream holding in fluid, so the fluid leaks out into the tissue. So it's quite complex. It can get even more complex, but I just want you to understand some of these general principles, and you'll see why in a couple slides. Active transport involves energy. An example of that is the sodium-potassium pump. That involves energy. 3 sodiums go out, 2 potassiums go in. Inside the cell is less positive than outside the cell. The outside is more positive. There are also channel proteins that let potassium out. So it's a very complicated process, but I'm sure in A&P you remember the concept of resting membrane potential. Well, this sodium-potassium pump contributes to that resting membrane potential, which is how some activation occurs within the cell. If you need more help, the Khan Academy has just some great videos. And they're going to go into a lot more detail, so you may not want to go to Khan Academy if you don't want more detail. But if you want more detail on this, then I would go to Khan Academy and search things like diffusion or active transport, and you'll see there's short little videos on that. The question probably in your mind is, so who cares? Who cares about this movement of fluid? Well, guess what? You're going to care. In a few minutes, you'll care about it. So I'm going to ask you a question. Why does gargling with salt water help a sore throat? Well, one of the reasons is, now it doesn't help if the throat's not swollen, but if the throat is swollen and you put salt in the back of your throat, what's going to happen? The salt is going to pull fluid from the tissues and reduce swelling. So that's just a simple example of fluid moving. The salt pulls the fluid from the tissues and reduces swelling. Let's look at something a little more significant, is heart failure and hydrostatic pressure. So the question is, why might right-sided heart failure, let me put the question up there, why might right-sided heart failure contribute to lower extremity edema? So if the right side of the heart is failing, that's the system where the return to the heart occurs. So if the return to the heart doesn't happen because of a buildup of pressure, where does that fluid go? So we have venous hydrostatic pressure is elevated. And because of that, fluid moves out of the blood vessel and may not be able to be returned to the heart. What happens at nighttime when people elevate their legs, they decrease some of that they increase that blood flow back and decrease the hydrostatic pressure. So if we go back, let's go back and just look and see if we can find the slide on hydrostatic pressure. Here it is. So if you increase the fluid in the vessels, so these are capillaries, but then they go to veins, that's returning blood to the heart. That capillary hydrostatic pressure gets greater, just like it might in a garden hose where you hold your finger on the end. That forces fluid into the tissue. All right, so that's the hydrostatic pressure. So that's why we care about some of these things. Let's get back to our other slide. Okay. So here's the patient with heart failure, has the peripheral, right-sided heart failure, has the peripheral edema. Patient gets edema. Okay. So I told you that if somebody's albumin is low, what happens? So that's the colloid pressure. So this shows the little protein molecules pulling fluid back in. If your protein level is low, so the question is, what is more likely to happen when a patient's protein level is low? That colloid osmotic pressure or oncotic pressure won't be there. Consequently, the person gets more edema. And that's the reason why. We just explained why. Okay. Now we're going to talk a little bit about some hormones that affect fluid levels. One is antidiuretic hormone. It affects osmolarity and osmolality. I will explain those terms. I don't think in these slides, but in class. Antidiuretic hormone acts on the kidneys. It's released from the pituitary. It's responds to the osmolality in the blood, and it makes the tubules more permeable to water. So what does this mean? If osmolality is high, so what does that mean to you? If osmolality is high, it's a high solute load, antidiuretic hormone is released and more water is absorbed. So it is antidiuretic, against diuresis. I don't know if I have the correct answer comes up here. Okay. So again, you have to understand if osmolality is high, it means there's a high solute load in the blood. It's going to say we need to water that down. And so we water it down by antidiuretic hormone talking to the kidneys and saying, you need to absorb more water. So that's the correct answer. The adrenals also play a part because they release aldosterone. Now that release is stimulated by several factors. Decreased sodium in the extracellular fluid, which is where the majority of sodium resides outside the cell. Increased sodium in the urine if your blood volume goes down. And what will happen is that this release of aldosterone will prevent sodium loss from the kidneys. If sodium isn't lost from the kidneys, then water isn't lost. So again, think about if you have a low blood volume and you want to increase your volume, one way to do that would prevent sodium loss. If you have less sodium in your extracellular fluid, the aldosterone will say to the kidneys, we need to retain sodium, and with sodium goes water. So that's the aldosterone. I'm going to show you this slide of the angiotensin system. And you've probably talked about angiotensin in pharmacology. Angiotensin 1 converts to angiotensin 2. That causes constriction of blood vessels and stimulates aldosterone release. That preserves sodium and water. So that's what we just said in the last slide. The aldosterone preserves the sodium in the water. Well, it preserves the sodium and consequently the water. Blood pressure will increase. So when you think about this, when you learn about ACEs or ARBs, what was going on? So let's look at the next slide and then we might come back. So an ACE inhibitor inhibits angiotensin converting enzyme. Can you think of an example, something like lisinopril? And then what does it do? So let's go back here. Angiotensin converting enzyme will block the conversion of angiotensin 1 to angiotensin 2. Consequently, this sequence doesn't occur and aldosterone is not released. Sodium is not retained. Not that no sodium is retained, but it doesn't cause an additional sodium to retain, so sodium is lost and water is lost. That helps someone's blood pressure go down. So that's how that ACE inhibitor works. Okay. Natriuretic peptides. So there's ANP and BNP. ANP is released by the atria. BNP is released by the ventricles. We generally measure BNP, and we use that in relation to people who have heart failure. These hormones, or these peptides rather, I'm sorry, they are hormones, respond to volume or pressure changes. And what they do is when they're released, they cause the kidneys to inhibit sodium and increase glomerular filtration rate, excuse me. So let me just give you an example of when we would use a BNP. So BNP is measured, it's a blood test that is measured in someone who has heart failure, and as their BNP goes up, that shows increasing heart failure because the ventricles are now stretched more than they were before. We're not going to spend a lot of time on the natriuretic peptides because you'll talk about this more when you talk about heart failure, which I think you cover in Nursing 295. So I don't want to spend a lot of time on it, but I want you to know that they're there. And if you look at them, I'm trying to see where in your book. I might have to put my glasses on. Hold on. I think they're addressed in your book somewhere. Natriuretic peptides. They talk a lot in your book about ANP, which really surprised me because what I've seen measured most is the BNP. It stands for brain natriuretic peptide. I guess somebody thought the ventricles were the brains of the heart, which I guess in some cases they are because they pump out the most that pumps out the most blood to the body, the left ventricle.